Hi, I'm Nick Chadwick. I'm a video engineer at Mux. And for the past couple of years, I've been working on kind of the intersection between video and machine learning, specifically using machine learning to improve video quality. We started at Mux using machine learning to try and improve our per title encoding to deliver better quality. But today, I'm actually going to be talking about super resolution. Now, super resolution is actually kind of an older technique, right? There are papers I found naming this from like the 80s, talking about how if you have multiple low-resolution frames with sub-pixel offsets, you can use that to create better-looking, higher-resolution frames. But I'm not going to talk about that at all today, because really what I'm going to be talking about today is super resolution, better scaling using machine learning. Now, the reason for this is that over the past few years, as machine learning has really taken off, the techniques for building super resolution algorithms have really just been completely dominated by machine learning, to the point where they're essentially becoming synonymous with each other, that there aren't any non-machine learning super resolution techniques that you really need to know about today. And this is a really exciting area. In fact, a couple of years ago, there was this huge acquisition by Twitter of this company called Magic Pony. And one of their main concepts and some of the demos that they showed was really using neural networks to improve images and video. And that hype has kept building, especially in the scientific community, that machine learning community. In fact, at Entire, the New Trends in Image Restoration and Enhancement workshop as part of CVPR, this year for the first time, there was actually a challenge specifically around super resolution for video. So in this talk, I'm going to start with a bit of an overview about why, as video engineers, scaling, specifically upscaling, matters to us so much. I'm going to try and give you an overview of super resolution, just one or two key papers that you need to be aware of if you really want to dive in and try this stuff out. And then I'm going to give you a demo of actually using super resolution so you can try it out yourself. And then I'm going to talk very briefly on what I think the future of super resolution is going to be and why I think everyone in this room really needs to start paying attention. Okay, so let's dive in. Why do we need to scale? That sounds like perhaps a simple question, right? Like, everybody knows we scale a lot, but really there's two reasons that we scale. The first is we scale down, then up as a low-pass filter in order to get better compression efficiency, better use of the available bit rates we have. And then more and more we need to scale up because we just don't have content. If you have a really nice library of 1080p content and somebody comes to you and says, hey, I want it all in 4K right now, like, you can't really go back in time and reshoot that content. You have to scale it if you want to create something in 4K or even 8K. Okay, so let's talk a little bit more about scaling down and up as a low-pass filter, because this is actually one of the key concepts about the convex hull. Some of you who've seen my talks previously will know I love reusing this slide, not just because it looks cool, but also because it helps highlight this notion of what the convex hull is. On one of my axes here, I have the resolution of the video. Another, I have the bit rate. And then I did a ton of encodes of a fairly low complexity piece of content showing what the resulting VMAF score or quality of that video was at each point. And then highlighted in red, you can see the resolution which maximizes quality for each bit rate along this curve. And inherent to this picture is that notion that we're going to need to do a lot of scaling. In fact, if we want to deliver a great 1K encode, we're not going to deliver a 1080p encode for this piece of content. So scaling lets us make better use of our bit rates, and it's one of the key insights underpinning that notion of what the convex hull is. So how do we scale, right? Like, what algorithms do we use? I mean, it's a solved problem, right? Just use bicubic. That's what Netflix says to do when you're reading their VMAF articles. Some guy on Stack Overflow is going to tell you to use lanczos. Let's test it out. So I'm going to take this specific piece of content at 1080p. Netflix made this available for free at a crisp 4K resolution. But for these tests, I'm just going to go from the 1080p resolution I'm going to scale down using a few different algorithms that you might encounter, and then I'm going to scale back up using bicubic. I'm not actually going to show you this result. I'm going to show you the data that I collected, which essentially confirms some of that insight, right? Nearest neighbor's down there at the bottom. Don't use that. Bilinear is way worse than bicubic, and lanczos does win by a teeny little bit. Then when we're going the other way, scaling up, I'm going to pick that best algorithm, lanczos. I'm going to scale up using a few different algorithms, and here's the resulting data for that. In this case, you can see again, lanczos is winning, bicubic is up there, nearest neighbor is doing something weird. I'm going to have to go talk to the Netflix people about that, and bilinear is worst. PS&R's got our back though, and we're just going to ignore that nearest neighbor line for now. But the point here is that when we are scaling, the choice of algorithm can have a huge impact in the resulting quality of our encodes. So you really do need to pay attention to scale. Okay, so what scaling are we using right now? Have you ever wondered? How do you find out? I wondered this a little bit and found that it was pretty tricky to actually figure it out. So I created this hell stream. I created a 360p image that, after scaling bilinearly versus bicubically, had maximum difference. For the machine learning nerds in the audience, my loss function was essentially the absolute error between the two images post-scaling. This slide is the result of upscaling using bilinear. And it gets brighter, hopefully you could see that, when we upscale using bicubic. So I can use this piece of test content to figure out what scaling we're using. Now, these two videos, this darker one and this brighter one, were both created using FFmpeg. Now I'm going to let whatever code path we're currently running through upscale the 360p version. And it gets darker. I already knew. I tested this in the menu. So right now, actually, even though scaling really matters to the quality of the content that you're seeing, in this particular path, we're using bilinear scaling. I tested this out. On my MacBook Pro on Chrome, I couldn't get it to use bicubic. On Safari, I got bilinear scaling, and then when I full screened and the last element slid off the screen, so it was only the video on the screen, only then did the algorithm pop in and switch to a better scaler. On Android, something similar. The new iPhones, you've got used bicubic all the way through. And you can test this out for yourself if you'd like. I've made this available. If you're really curious, go find the recording of this talk afterwards. Grab that video for yourself. And you can use it to test what scaling is being used. And right now, it's kind of a patchwork. And we're not even always using the algorithms that are decades old that we know are best. And it's with that in mind that I hope you're excited and interested about scaling, because now I'm going to talk about the future of scaling, which is super resolution. Okay, so I'm going to start with two key papers. Now, there's lots of awesome work that's been done in this area, but there are two papers that you really need to be aware of if you want to understand where the research is going. These are the ones that get cited the most. The first one, and the one that really kicked off a huge amount of interest in super resolution, was this paper, Image Super Resolution Using Deep Convolutional Networks. Now, you might be thinking, well, if it works, if it's images, why do we care? Well, video is just a series of moving images, right? To fake the appearance of motion. And it works really well for video, too. The key insight behind this paper was that, unlike some of the previous approaches of marrying machine learning and convolutions with upscaling, this used multiple convolutional layers to create a feature map, an intermediary representation of the video, which would then be processed again, and then once more before creating the final image. It kind of looks like this. I'm not going to dive too deeply into the math here, but essentially a convolutional filter is learned and run over the input to create a set of feature maps. Then another convolution is run on that, and one again. And using this approach, this paper was able to show remarkably good results, even on single images, at doing better upscaling. Now, remember I said Twitter made that giant acquisition? Well, those guys also released a really interesting paper. This paper was originally a Magic Pony paper and is now a Twitter paper, essentially. And in this paper, the authors really talked about how if you actually change the way you think about it, you can do super resolution in real time. This image is actually a little misleading because the low resolution input that's going in at the start is actually the same resolution as the output. It's just upscaled using something like bicubic or bilinear before being reprocessed. This paper had a key insight that by doing most of the work down in the low resolution space and then learning how to do the upscale most effectively, you could both reduce the number of computations and improve performance at the same time. They had this notion of a deconvolution, which is a fancy way of saying that you can reshape matrices if you want. They have this image trying to explain some of their insight there, but really the important part here is that at each step along the way, this network is able to be trained fully, going from low resolution to high resolution. Okay, so with that brief overview, let's actually try it. You might have seen an image like this before if you've ever looked into super resolution saying, wow, look, super resolution, it's really cool. Look at it. No, we're at Demuxed. We're going to dive in and get our hands a little dirty. And there is an FFmpeg filter now that does super resolution. And that's the one we're going to use. Although the documentation is a little sparse. Basically, this came about from a Google Summer of Code project last year. There was a call put out to build super resolution into FFmpeg. And technically, the project was a success. Sergey Lavrushkin took up the call and got his super resolution patches merged in. So let's try it. It'll work something like this, right? We'll use FFmpeg. We'll give it a 540p input. We'll say that we want to scale using this SR filter, and we'll get a nice crisp 1080p video out. Well, it's not quite that simple. In order to use this SR filter, we do need to get one step deeper into understanding a little bit about how machine learning works. Essentially, we need to decide what the model is that we're going to use as part of this filter. So all the super resolution papers that make an impact get a fancy name. The first one is SRCNN, and the next one is ESPCN, the Efficient Subpixel Convolutional Network. And then once we've chosen what model we're going to use, we then need to train that model to create a set of weights. Those are like the actual values that are going to go into the matrix multiplications that we're going to use as part of running this algorithm. Okay, there's a really interesting observation we can make there, which is if we're training, what are we training on? Our choice of inputs actually affects the performance of the resulting model. If we want to just build a better bicubic upscaler, we can choose a varied range of content, train this neural net on that content, and get something that can do a better job. But we don't have to. We can actually choose a single content type. I'm going to show you an example in a second of just NFL content. And we can build content-specific scalars that are able to do a better job on certain content types at the expense of others. Okay, so it's really simple. You just clone the repo, you put your content somewhere, you run a Python script and cross your fingers that you've got the requirements in the right place. You've got TensorFlow, you've got OpenCV, you run this training script, crossing your fingers again, you run Python 3 to generate a header and a model after it. Yeah, I'm going to leave this slide up a moment because if you want to try this at home, this is kind of what you're going to have to do. But the kind of point I'm making here right now is it's rough. And it doesn't work the way you might initially think it works. It only works on a single plane of video. So if you like grayscale video, cool. But if, like me, you can perceive color, you might be a little disappointed by the results. So here's an example. Again, I don't really expect you guys to get anything from this slide. I'm leaving this up for a moment so you can come find this in the recording if you want to try this out for yourself. Because you're going to need to take your input content, you're going to need to split it into multiple planes, you'll need to pass only that Y channel through the super resolution filter, then you need to independently scale the U and the V, merge it all back together, and then encode your output. Okay, so after we've done all of that, we get results that kind of look like this. And at this stage, I need to point out that this venue is really, really awesome, but this screen is not actually 1080p. That's a problem if you're trying to give a talk on how scalars work. So take a look, if you can, at things like the AT&T Stadium sign, the great Harmonic logo. Thank you for making this content. And we can also take a look at things like the numbers on the jerseys or faces. Hopefully you can tell that this filter is doing a better job. Okay, I'll let it run for a moment. And for the people who can't quite see the side screens, I'll do it again. This time I took a subregion, blew it up, so it's a little harder to see what this video actually is, but hopefully it's a little easier to see what the actual effect is, where our super resolution filter is actually able to do a much better job picking apart some of these edges and crisping them up. But don't just take my word for it. Of course, I'm going to invite VMAF to this party and see what it thinks. In one moment, I just want you to take a look here. Numbers on jerseys. Cool. It's better. It's better almost across the board. We get about 5 additional points of VMAF. But super resolution can actually do a much better job on some content types than even this. And that's why anime has been actually early adopters, as usual. And things like text or video games get a huge boost from this too. And for the animators in the audience, I'm sorry I didn't mention Waifu 2X sooner. It's got a bit of a goofy name, but it is a good implementation of super resolution, especially that initial paper. They have this example on the website of comparing lanczos 3 scaling to Waifu 2X, and you can see that things like the lines are a lot crisper. Okay, but it also works great on video games. Let's take a look at that too. Here you can see things like the numbers on the mana bars, the numbers at the top of the screen. There, this one's a little cut off. And there's going to be some text that pops on in a second, which should show up pretty nicely. And once again, not quite a 1080p screen, so let's blow it up a little bit. And here you can really see that whilst this network is overshooting a little bit and adding in some little speckles here or there, it does a much better job at picking apart things like text and details, and really allowing you to view this content a little more easily. And this is just built into FFmpeg. You can just go and use this right now. Once again, VMAF agrees with us. In this case, we're getting a full 10 VMAF point bump just from switching out the upscaling algorithm that we're using to a super resolution algorithm. Now, once again, keeping myself honest, here's how I created these test clips using the FFmpeg filters. Again, I don't expect you to parse this right now. I'm just going to leave it up on screen, so for those of you in the audience who are really excited about trying this out, you can keep me honest and generate these test clips in the same way that I generated them, and see this effect for yourself. Okay, sure, so super resolution is awesome. What's the catch? Well, it really kind of needs a GPU if you want to run it on real time on clients, and the code is kind of crazy hard. Not a huge amount of the research that's been happening in academia has come out of complicated Python scripts to easy one-click engineering solutions. Super resolution isn't quite as immediately cool as deepfakes are, so there's no open source tool where you just pop in a video and get a better one out. Again, Waifu 2X is cool, but by default it's trained on specifically anime content. And for why it needs a GPU, this is kind of a rough estimate of the number of floating point operations you would require if you wanted to do nearest neighbor, bilinear, or bicubic upscale. Now, I'm not entirely an expert on the AVX instructions you can use to make bicubic scaling faster. I'm just giving you this as a rough estimate to compare it really with this. Super resolution takes another order of magnitude more processing in order to create these amazing results. And I know what you're all thinking, worth it. But a lot of customers occasionally complain when we melt their phones. So it's definitely ready for server-side use, and especially as more and more use cases come in where we're trying to deliver 4K or 8K content that we might not even have, super resolution can step in as a way better bicubic upscaler. It beats lanczos 2. But it's not quite ready for clients, although that's changing. Recently, at the All Things RTC conference, Agora.io demoed on stage their real-time super resolution filter for improving the quality of voice calls. And again, you can kind of think about that specific content type. Faces in front of a mobile phone screen, talking to another face on a mobile phone screen, is a really great use case for training a content type specific upscaler. So let's talk about the future. Because actually, everything I just talked about is in the past. Everything that I've demoed, the concepts are over 3 years old. And in that 3 years, there has been a lot of progress. There's been progress in making super resolution faster. Papers like XUnit, talking about how to change the activation function away from ReLU and using more Gaussian process so that using the same number of computations, you can better utilize your network. Or large receptive field networks, talking about decoupling the convolutions in X and Y domains, essentially using more intermediary representations, but lowering the number of computations that you need to do, trading off memory and CPU cycles for similar performance. There are also papers strictly about making it better. You can invite adversarial networks to this party and make super resolution algorithms that perhaps don't perform as well in terms of PSNR, but perform better as far as human observers are concerned, doing a better job at removing some of those speckling artifacts you might have seen in the previous demos. There are also papers about using spatiotemporal networks, actually kind of closing the loop with the original research and using multiple low-resolution frames, using some motion compensation on those frames, and then training algorithms that can use multiple input frames to create a single output frame that looks way better. There are also some papers that blur some of the boundaries, and by boundaries I mean real-time style transfer. Remember, like, Prisma was on everyone's phone making those really cool images? And also, adversarial networks and style transfer sound a lot like deepfakes. The same technology that's going to be making deepfakes work even better is also going to let us create even better looking video. But with all of this, there aren't actually that many implementations client-side that you can go and use right now. So as a proof of concept, I'm not a great GPU or machine learning programmer, but I wanted to understand whether or not these techniques were feasible to run client-side at all, if just the naive implementation I was capable of could run. And it totally can. So I've managed to convince my employer to let me open source a Video.js plugin that will let you actually use super resolution in your browser. It's going to it uses WebGL to run super resolution in real time. I was hoping to open source it today and be like, it's cool, go check it out. It's not quite ready. There's one or two things I need to clean up. But it is integrated with Video.js. If your browser supports WebGL and has a reasonable GPU behind it, you should be able to at least see super resolution running in real time and try it out for yourself. And I'm going to try and make it a little bit easier to generate some of those models so that you can actually get up and running in a little bit more straightforward way. So come find me for a demo. It'll look something like this. This is just Video.js with a little slider. You can slide back and forth. I'll be sliding it for you and getting excited. Thank you so much. I'll be hanging out at the Demuxed booth today when I'm not listening to awesome talks. Thank you.